Just 1 minute to go.
Recording in progress.
Okay, now everything will be recorded.
Good recording. I don't have any seconds.
So, I mean, maybe I say just a few words and then maybe Gianluca could say something if he wants. So I just want to say that, that we are 45 45 speakers in this seminar. So it's not bad this year, I think. And I hope you all leave some time at the end for some questions and we have a bit of discussion. And of course, I'm this year also happy to have 2 co-chairs. And I think Gianluca is here, and maybe Gianluca, you show your face and also say, because you've been responsible for the first day and tomorrow morning. Maybe you want to say something, Gianluca?
Yeah. Hi, everybody. And yeah, thanks, Christoph. So we have 2 sessions today and 1 tomorrow morning, which are mainly devoted to experimental progress on high field physics using lasers. So it's a pleasure to have Sergey Bulanov here to chair this first session, which includes 3 talks. Then we'll have a short break, and I will chair the second session with another 3 talks. So again, thanks very much for attending, and Sergey, it's all yours.
Okay, thank you. Thank you. It's a pleasure to be chair of the first session. And as Jean-Luc already said, we have 3 presentations. And first will be done by Eva Loss about observation of electron energy loss in strong fields. And she will explain how it has been done and what is Bayesian inference, I expect. Please do it. 30 minutes you have.
Great. Okay. Well, thank you very much for the introduction, Sergey, and thank you to the organizers for inviting me here today. I'm going to be presenting the work that I've done on observing electron energy losses in strong fields with Bayesian inference and using model selection. So first of all, I'd like to thank all of my collaborators. This was a really large collaborative effort from involving people from a number of universities. So just a big thank you to everybody who's listed here. This work would not have been possible without them. So my work is primarily focused on radiation reaction. So radiation reaction is the recoil that a charge experiences upon emitting a photon. It's expected to become a significant effect for electric fields which approach the Schwinger limit. So this is defined as the field strength which can that can induce pair production from vacuum. So we expect that fields of this magnitude will be generated in certain astrophysical environments, such as by pulsars and quasars, and they may also be rendered accessible by the next generation of high-power lasers. So if we wish to understand charge dynamics, radiation production, and other subsequent related processes, such as pair production in these environments, then it's important for us to also understand radiation reaction. So in this talk, I'm going to look at 2 models of radiation reaction. So this plot illustrates the predictions that each of these models make. So I'm going to look at a classical and a stochastic model. So in this case, I've simulated a Gaussian electron spectrum, which is shown in orange. I don't know if you can see my cursor, maybe. Well, hopefully. So I've simulated this Gaussian electron spectrum colliding with the counterpropagating laser pulse. And then the classical prediction for the post-collision spectrum is shown in green, and the stochastic prediction for the post-collision spectrum is shown in red. And so you can see that the classical model predicts higher energy losses than the stochastic model, and it also predicts spectral narrowing, whereas the stochastic model predicts spectral broadening. So these are the key differences between the predictions that each of these models make. So we had 2 aims in our most recent experimental campaign. The first was to try and observe radiation reaction. One of the key hallmarks of radiation reaction is that the electron beam experiences a net energy loss. So this is one of the things we wanted to determine. And then if we were able to do that, then we aimed to try and identify which model of radiation reaction was most consistent with our experimental data. So this is an overview of the experimental setup that we used. We conducted an experimental campaign back in 2021 at the Central Laser Facility. So this was a dual beam experiment. So we started off, we used an F40 parabola to focus a laser pulse into a gas jet target. So this drove a wake field, which accelerated electrons up to about a GeV. And then we had a second counter-propagating laser pulse, which was focused by an F2 parabola onto the end of the gas jet, where it scattered off the electron beam, which then produced gamma radiation. So then the electron beam and the gamma radiation propagated through a hole in the F2 parabola through a permanent magnet, which we used to sweep the electron beam onto a set of Lanx screens, so we could measure their energy spectrum. And then the gamma radiation was incident on two cesium iodide diagnostics. So the first was an array which we used to characterize its transverse profile, and the second was a cesium iodide stack, which we used to measure its spectrum. So there have been, so this work builds on two previous experimental campaigns, which were conducted by Cole and Poda back in 2015. So one of these campaigns, which was led by Cole, found evidence of a radiation reaction with 3 sigma significance. And they concluded that their data was more consistent with the stochastic model of radiation reaction than the classical model, but only to 1 sigma significance. The second campaign by Poda also observed signatures of radiation reaction to less than 2 sigma significance, but they actually found better agreement between their data and the semi-classical model. So I haven't discussed the semi-classical model in this talk, but basically it's a halfway house between the classical and stochastic models. It predicts similar energy losses to the stochastic model, but it predicts spectral narrowing, similar to the classical model. So the sort of the results that these two experiments have generated leave some outstanding questions regarding which model of radiation reaction is valid and in what regime. One of the difficulties that both of these campaigns struggled with was that they were only able to take a limited number of successful collision shots. And so they drew their respective conclusions with a low degree of significance as a result of that. And this was something that we were hoping to maybe improve on. So one of the difficulties that we have in this experiment is that we're not able to measure the pre-collision electron spectrum. But in order to determine whether we've observed radiation reaction, we need to know whether the electron beam has lost energy. So how do we do that if we don't know what the pre-collision spectrum looks like? So essentially what we do is we try to characterize the electron beam statistically for successful collisions, and then we compare that to the distribution of electron spectra that we measure for unsuccessful collisions. And we try to see if there's a difference between the electron energy between these two distributions. So this means that we need to identify hits and misses. So to do that, we use our gamma profile diagnostic, which was the thin cesium iodide array that I showed a couple of slides back. So basically, we expect the background signal that we measure on this diagnostic to scale with Q gamma squared, where Q is the electron beam charge and gamma is the Lorentz factor of the electron beam. And so we characterize the scaling by taking several data sets where the counterpropagating laser is turned off. And then, so this background scaling is shown in this figure here on the left-hand side. And then we say that for our shots where the laser beam was turned on, if the yield on the gamma profile lay within 1 sigma of the background scaling, we say the shot was a miss. And if it was 3 sigma or more above the background, then we say that it was a successful collision. And so the plot on the right-hand side here shows the successful collisions and the misses that we've identified in that manner. Note that this plot is on a log linear scale, so although it isn't necessarily easy to see it from this scale, actually most of the successful collisions have produced gamma profile yields that are at least 2 orders of magnitude brighter than the unsuccessful collisions. So once we have these two populations of hits and misses, we can compare the characteristics of the electron beam for both of these populations. So I'm showing a histogram of the mean electron energy for the hits and the nulls here. And you can see that generally for many of the hits, the electron beam energy is actually lower than it is for the nulls, which would be consistent with a downshift in energy, which we expect to see if radiation reaction has taken place. But we want to know if this is statistically significant or not. And so to do that, we perform a 2-sample KS test, which yields a p-value of 2 × 10⁻⁶ under the null hypothesis that the hits and the nulls are drawn from the same distribution. So this means that we can reject the null hypothesis at the 4.7 significance level. this is promising, but we can actually identify an additional metric of whether or not the electron beam has lost energy, and this pertains to the shape of the electron spectrum. So we expect that radiation reaction will disproportionately affect the most energetic electrons. So these will radiate a higher proportion of their energy. So here I'm showing the electron spectrum that we've measured for an unsuccessful collision in black. And this has a peak at around about a GeV. And this is compared to an electron spectrum for a successful collision, which is shown in red. And here the height of that peak is a lot lower. If this is if this null shot were to be indicative of like a typical pre-collision spectrum, then this might show that charge is downshifting in energy, but it's specifically the charge at high energies that is being redistributed over the rest of the electron spectrum. So the shift in peak height can also be considered to be a metric of radiation reaction. And so our second metric is the maximum height of the electron spectrum above the 70th percentile. So that's demarcated by these two like crosses here. So then I again plotted some histograms of this of the maximum height of the spectrum above the 70th percentile. And in doing so, I obtained these two histograms for the hits and the nulls. And again, for the hits, so you can see that the height of the peak is lower generally for than that of the nulls. And this could be indicative of charge being downshifted in energy from high energies to low energies. So a reduction in the proportion of charge at the highest energies, which is also consistent with radiation reaction having occurred. So again, to see whether or not there are significant differences between these two populations, I performed a two-sample KS test, which yielded a p-value of 1 × 10⁻⁹ under the null hypothesis that the hits and nulls are drawn from the same distribution. Again, this is a highly significant difference between these two distributions. So we know from the analysis that we've done that the mean energy of the electron spectrum and the height of the high energy peak are expected to vary independently of each other due to shot-to-shot fluctuations. And so we can obtain the probability that these two metrics have varied independently and simultaneously by multiplying the two p-values. And this gives us an overall p-value of 2 × 10⁻⁵ under the null hypothesis that the hits and misses are drawn from the same distribution, which means that we can reject the null hypothesis at the 7.9 sigma level. So this is a very high degree of a very highly significant set of differences between the electron spectra that we measure on our hits and nulls that is consistent with radiation reaction having occurred. So that was an overview of the first of our two aims, and now I'm going to move on to the second, which is to try and identify which model of radiation reaction best explains our observed data. So to do this, I use something called Bayesian inference. So let's say that you have a data set and you have a model that you think might describe your data, and your model is parameterized by a set of parameters whose values you don't know. Ideally, there are three things that you want to do. You'd like to infer the values of the parameters that produce the closest agreement between your model and your data. In performing this inference, you also want to take into account any uncertainties that may have been present on the experiment. And thirdly, you want to calculate the probability that your model is accurate given the data that you've measured. So Bayesian inference allows you to do all of these things. So it's a very useful tool for us. It utilizes something called Bayes' theorem, which allows you to write the posterior probability in terms of a prior and likelihood probability, like the product of those two probabilities. So the posterior is a quantity that we don't know how to measure, but we're interested in. It's the probability that our model is accurate given our data. The likelihood is something we can calculate. So this is the probability that you observe your data given that a particular model is accurate. And your prior probability includes any information that you've measured or anything that you may know from theory or simulation about the parameters that you wish to infer. So this theorem is useful this sort of theorem is used by the Bayesian inference statistical technique, which we apply for radiation reaction for a number of reasons. One of them is that when we have these experiments where we collide an electron beam with a laser pulse, there are lots of collision parameters which determine the electron beam energy loss, whose values we don't know, but we need to infer them because they affect our final result. So this statistical technique allows us to do that. It's also useful to us because it allows us to include any sources of experimental uncertainty naturally. It also allows us to fold in known or prior information into the inference. So, for example, if we measure the energy of the laser pulse, we can use this to constrain what the intensity of the laser might have been at the focus or at the collision. We are also able to use this technique to combine multiple diagnostics. So, for example, the electron spectrum, the spectrum of gamma radiation can both be included in a single self-consistent framework. And finally, a Bayesian framework allows you to obtain a quantitative metric, which will let you compare different models. So we can use this to compare different models of radiation reaction. The algorithm that I've used to implement Bayesian inference is called a Hamiltonian Monte Carlo, which we've chosen for its efficiency. So on this slide, I'm just going to give an overview of how that algorithm, the Hamiltonian Monte Carlo, actually works. So let's say that you have a data set that looks a little bit like this one, and you have a few ideas for some models that may fit it, but you don't know which one is the best. So you start with a linear model, and you feed this data and your linear model into your Bayesian Hamiltonian Monte Carlo. And your algorithm then looks through your parameter space and it tries to identify the combination of those parameters, your linear parameters, that optimizes the posterior distribution. And then when it's found that optimum, it sort of oscillates around it. And then you can take the values of the parameters that it sort of returns at that optimum, and that gives you these two distributions where the width of the distribution reflects the uncertainty in the inference. So once you have those, you can then return those values that you've inferred back into the linear model, and each combination of values will give you its own unique linear fit. And so you can summarize that distribution of linear fits that you obtain as a result with a mean and a standard deviation. So we've done that now, and you can see that a linear fit was a terrible idea. So let's say that I then replace that with a quadratic model. So I repeat the entire procedure, and that gives me this resulting curve. So now that we have two models that we're using to fit our data, the question is which of these models is performing the best, and how do we determine that quantitatively? Because we can see it by eye, but a quantitative metric would be useful. So to do this, you can use something called a Bayesian information criterion. So this is defined here. It's a metric that contains two terms. The first term is essentially a penalty term. So it implements Occam's razor. And it penalizes overfitting. So it will penalize the number of, it will introduce a penalty that is weighted by the number of fitting parameters that you use. The second term is the negated log of the likelihood. So the likelihood is the probability that you observe your data given that your model is accurate. So this means that when you're comparing different BICs, the BIC that is closest to minus infinity is performing the best. So if you have two models to compare, you calculate a BIC for each of them, and then you take the difference of those BICs to see which one is performing the best. This table summarizes how you interpret that difference in BIC. So if you have a difference in BIC of between minus and plus 2, neither model is favored. If it's greater than 2 but less than 6, you favor model 1. If it's greater than 6, you strongly favor model 1. So if we look at how this pans out for our example with the linear and the quadratic curve, I obtain a difference in BIC of minus 200, which means that the quadratic model is strongly favored, which is just as well because that's the model that I used to generate the data. So it's, looks like it's working, which is great. There's one more thing that I can sort of say about the difference in BIC that is maybe helps make things a bit more intuitive. So the BIC depends on this log likelihood term, which means that the difference in the BIC depends on the log of the likelihood ratio. So this means that you can interpret a difference in BIC of 1 as a difference in relative probability of e to the 1. So in this slide, I'm going to sort of summarize the way that I implement a Bayesian framework for radiation reaction experiments. So as I mentioned earlier, we're not able to measure the pre-collision electron spectrum. And so instead we generate predictions for this using a neural network where the width of the distribution of predictions gives you some idea of the uncertainty in the prediction. And this neural network is discussed in far more detail in Matthew Streeter's paper, which was published this year in High Power Laser Science and Engineering. So please give it a look if you're interested. So once we have this distribution of pre-collision electron spectra, I perform a Gaussian decomposition. So I split them up into little Gaussians, and I feed that into my Hamiltonian Monte Carlo algorithm, which selects some fitting parameters. So the parameters that I'm fitting specifically are the normalized vector field potential, so the laser A0, the longitudinal offset of the collision from focus, and the electron beam duration. So with those three parameters, I can reconstruct the pre-collision phase-space distribution of the electron beam, and also the intensity of the laser that each sort of electron bunch collides with. And then I put that information into a forward model. So this forward model is something that I've written myself in C++. I benchmarked it against QED Cascade. I had a lot of help from Chris Aaron for that, so a big thank you to him. So this forward model allows me to predict the post-collision electron spectrum and the post-collision gamma spectrum. And then I put that information, I compare that to the measured post-collision electron and gamma spectra, and that provides me with a value of the posterior for these specific combination of parameters. So that value of the posterior then informs where the Hamiltonian Monte Carlo algorithm will sample next, and it continues to look around the parameter space until it converges on an optimum. So to see how well this inference procedure works, I tested it on some fake data, so some simulated data. So essentially what I've done is I've started with this distribution of pre-collision spectra that were predicted by the neural network that I mentioned earlier. I select one of them, and then I choose the A0 of the laser, the longitudinal offset from of the collision from focus, and the electron beam duration. And then I run a simulation of the collision using the stochastic model of radiation reaction. And that gives me this post-collision spectrum for the electron beam, which I'm showing here in red, and also a post-collision spectrum for the gamma beam, for the gamma radiation, which I'm showing in the right-hand figure, also in red. Then I run the Bayesian inference procedure twice, once for each model of radiation reaction, and I'm showing the results for the stochastic inference in magenta and the classical inference in green. So I describe this test case as an ideal test case because all of the physics that I've incorporated in this simulation has also been included in my forward model. So in principle, the Bayesian framework should be able to return all of the sort of expected results because there's no missing physics. So you can sort of see by eye that the stochastic model is performing better than the classical model. It retrieves a more smooth profile that's closer to the simulated data. So this is encouraging. It indicates that the model that we expect to be performing well is indeed doing better, but we want to assess this quantitatively. So here I look at the collision parameters that each of these models have inferred. So in the plot on the left-hand side, I look at the mean effective A0. So this combines the longitudinal offset of the collision from focus with the laser A0. So I look at that parameter and also the electron bunch duration. And so the classical and stochastic results are shown in green and magenta, and the input parameters are shown here in red. And so you can see that the stochastic model is able to retrieve the correct collision parameters to within a standard deviation of the true ones, whereas the classical model is significantly under-predicting the mean effective A0, and it's over-predicting the electron bunch duration. So the reason why it's doing this is because, firstly, the classical model predicts higher energy losses for the same collision parameters than the stochastic model, which means that in order to obtain the same or similar energy losses, it has to reduce the intensity of the laser at the collision. So that's why it predicts a lower effective A0. And then it also predicts a higher bunch duration because it predicts spectral narrowing, whereas the stochastic model predicts spectral broadening. So the classical model stretches the electron beam out over a wide range of A0s so that the electron beam experiences different ranges of different energy losses. And this means that it ends up with a broader and smoother post-collision spectrum than an on-axis, than a short duration electron bunch. So because the classical model is using these parameters, it's inferring effective parameters which don't resemble the input parameters. it's sometimes useful to summarize, to treat these as like effective inferred parameters, and to summarize them, to use them to calculate instead like a distribution of eta, where eta is the quantum parameter of the electrons. So eta is like defined here, and you can see that it like depends on the Lorentz force that the electron beam experiences. So it's like a measure of the instantaneous acceleration that the electron beam experiences in an external field. So for each collision, there's a distribution of eta because each electron has a different energy and interacts with a different field strength. And so you can summarize that distribution with a mean and a standard deviation. And I've shown those in this figure here. So the stochastic model, again, comes within a standard deviation of the true parameters, whereas the classical model is further away. So this is consistent with the left-hand plot. And finally, I can compare these two models quantitatively by computing a Bayesian information criterion for each of them. And when I take the difference of these, I get 62, which means that there's very strong evidence to favor the stochastic model, which is also the model that we use to generate the data. So that's promising. It shows that we retrieve exactly the results that we expect to retrieve. So the framework is working. The second thing that I did, so in our experiments, sometimes we have like additional sort of complications that may not be included in the forward model. And so I wanted to know how robust my forward model was under some of those like potential complexities. So again, I've run another simulated test case, also assuming the stochastic model. But in this case, I've introduced a transverse offset between the focal like point of the laser and the collision position. So the effect of introducing a transverse offset essentially means that the electron beam interacts with a wider range of A naughts because of the radial dependence of the gradient of the laser intensity. So this means that, compared to an on-axis collision, an electron beam will see like a wider range of laser intensities. So once again, I run the two inference procedures, one for the stochastic and one for the classical model. So the sort of interesting thing about these two inferences is that for the simulated data, in the pre-collision spectrum, there's a peak at about 0.9 GeV, which has been sort of reduced in height and smoothed out in the post-collision simulated data. For the two inferences that I've run, the stochastic model is able to capture that peak, whereas the classical model sort of gets the downshift in energy right, but it doesn't get the reduction in peak height. So it looks by eye as though the stochastic model is outperforming the classical model. But we also want to know what parameters these models are inferring, and so those are summarized in this slide here. So the stochastic model this time does a lot less well than it did before. It is able to retrieve the mean effective A naught within a standard deviation, but it massively overpredicts the electron bunch duration. Whereas the classical model is actually like it does underpredict the mean effective A naught, like it's not quite within an error bar, but it does get the electron bunch duration correct. So that's interesting. So what we think might be going on here is that the stochastic model is trying to compensate for the broader sort of distribution of A naughts of laser intensities that the electron beam is interacting with, and the resulting sort of spectral broadening that we get from that by stretching the electron beam out longitudinally instead of stretching it transversely. So we think that the stochastic model is inferring like an effective electron bunch duration, which it's using to compensate for physics that was not included in the forward model. The classical model, once again, is underestimating the mean effective A naught because it predicts higher energy losses than the stochastic model. So one way that one sort of sanity check that we can do is that we can once again retrieve or calculate the distributions of eta and then summarize those with a mean and a standard deviation. So this will tell us more about what is like physically happening in the collision. And when we do that, we actually see that the stochastic model is outperforming the classical model. So it retrieves a mean eta within a standard deviation. And it also is like closer to getting the correct sigma, although it doesn't quite get within a standard deviation. It's like a few standard deviations out. And we think that this is happening because there are only 3 degrees of freedom in my model, and I'm not including like the physics of the transverse offset. So I think that it doesn't have sufficient degrees of freedom to fully reproduce the distribution of eta. So this is as close as it can get, basically. So then we want to compare the two models quantitatively. So the delta BIC that I retrieved for that is 0.96, which means that there's insufficient evidence to favor either model. So what this tells us is that if our collision is sufficiently non-ideal, so if it includes physics that we haven't included in the forward model, we may lose our ability to distinguish between different models of radiation reaction. So now I come to the point where I apply my Bayesian framework to experimental data. So I've applied this to 9 shots that we took on the experiment, and I'm showing the results of 2 of those inferences here. So in the first figure, well, actually in both figures, you can sort of see that both of the models are performing fairly well. In the first figure, the stochastic model seems to do a better job of getting the average height of the electron spectrum right, although it sort of misses this high energy peak. In the second figure, for a different shot, both the stochastic and classical model overpredict the energy losses of the electron beam, but the stochastic model overpredicts this to a lesser extent. So what we really want to know, of course, are the inferred parameters and how well each of these models are performing for this data. So once again, I show the electron bunch duration plotted against the mean effective A0. And you can see that, as in the test cases, the stochastic model tends to retrieve higher mean effective A0s than the classical model. So that's consistent with our expectations from theory and also our previous test cases. However, in this case, the classical model and the stochastic model seem to infer mostly similar bunch durations, with the exception of 2 or 3 shots. So these bunch durations are actually a lot higher than we expect them to be based on simulations that we've run. So we think that what's going on is that, as with some of our test cases, we think that the inferences here are stretching the electron beam out so that it interacts with a wider range of intensities to compensate for some of the physics that isn't included in our forward models. So again, in order to get a better idea of what's actually happening in the collision, we look at the distribution of eta and its mean and standard deviation. And in doing so, we find that, as expected, the stochastic model tends to retrieve higher mean etas. But interestingly, there's also a strong linear correlation between the mean eta and the standard deviation of eta that we obtain. And we think what's going on here is that as the inference procedures stretch out the electron beam to try and access a wider range of laser intensities. Sorry. Oh yes, I see. I'm over time. I'll finish.
You're out of time.
Thank you.
How much time do you need more?
Maybe a minute. Yeah, I'll be fast. Sorry about that. So we think that what's happening is that as the inference procedures stretch out the electron beam, they also have to bump up the mean eta that the electron beam interacts with to try and recover the energy losses that we observed. So the final figure just shows the BICs that I get for each of these models. And you can see that the stochastic model consistently outperforms the stochastic model, the classical model, because it for every shot it produces a BIC that is closer to -infinity. So when you sum over these difference in BICs to obtain and you add the penalty term to obtain a final delta BIC, we get 60.2, which means that there's very strong evidence to favor the stochastic model over the classical model. I'm going to leave my conclusions up. Sorry for going over time. Thank you for listening.
Thank you very much. Actually, we don't have a time for question, but I see Shai Pomeranz wants to say something. Try to formulate the question and the answer.
I'm sorry, I was just doing the clapping motion. I do have a question, but I can give it up if.
Okay. Then no question, and what?
Wait a moment.
Okay. So
can I ask one? Can I ask one, Sergey?
Say.
Can I? Okay.
Yeah.
No, okay. So sorry, I didn't find where I pushed for the question. So I just wanted to. This was very interesting. I mean, it's a very sophisticated comparing of the models. I mean, this is, I think, very, very clear mathematically. The only thing is for these, I mean, it's of course a bit not so surprising, right? The stochastic model is better than the classical model. Could you say a bit of some of the weaknesses of the stochastic model? I mean, sometimes, because when we compared in the old days the quantum models with semi-classical models, the problem was that these sophisticated quantum models, they had weaknesses, like they're not beyond the constant field approximation. So those things. Are there any weaknesses in this stochastic model? I didn't see much of how much was.
So this is a good question. I haven't really discussed the weaknesses of the stochastic model because we're not really this data isn't really in the right regime for that. So this is based on the locally constant field approximation. And so like the stochastic model, actually all of the models that I'm considering become less valid for like A0 is around about 1. But actually the A0s that I'm inferring are like quite a bit higher than that. So we should be like out of that regime. But of course, this is one of those things that would be useful to verify with like an actual parameter scan experimentally, so that we can see exactly where it starts to break down and, to what extent we can trust its accuracy.
So it could be that other models without stochasticity are maybe better because they don't have to do those approximations. That's always the problem, right?
So it sort of depends because the classical and the semi-classical models that I'm using also use the locally, like they use the LCFA as well. So the stochastic model is going to be wrong for that reason, then so will the other two models. But possibly other models that don't use that approximation, like the LMA, the locally monochromatic approximation, that may be like it's possible that may have greater validity, depending a bit on the specific like
that would be useful. That would be useful to apply, I guess, right? I mean, to see.
Yes, and we
get even better agreement with the data. Okay, just was
that's also something that we're very much interested in looking into. Yes.
Otherwise, very interesting. Okay, thank you.
Thank you.
I think we should thank you for your presentation again. And now we should listen to Dino Yaroshinsky's presentation about transient plasma photonic structures as robust optical elements. Dino, I saw you.
Thank you very much. I'll just share screen.
But I don't know where we see Ishai Pomerantz instead of your presentation.
Can you see my screen or not?
Now, yes. Now, yes.
Okay. Okay, very good.
Good. You have 30 minutes, as you know.
Yes. Okay. So slight shift in the in topic. So what I'm going to talk to today is about how we can create optical elements out of plasma. And I'm going to tell you a little bit about how to make, so these are diffractive structures out of plasma. They're transient, they only last for a few picoseconds, and they are time dependent, which is quite interesting. They can be 1, 2, or 3 dimension. And the whole motivation for this is, can we use these as optical elements in advanced laser technology, to make the mirrors and compressors, etc., much more compact. And also to look at new states of matter, for example, time-dependent systems with time-dependent permittivity or time boundaries. So we all know the laser-plasma interaction. We heard the previous talk, producing particles, high-energy particles. We can also use them for the laser-plasma interaction to amplify light and also produce secondary sources, and Compton backscattering is just one of these secondary sources. Of course, being investigated for basic, understand the basic interaction. And also beams can be used as drivers for coherent radiation sources, for example, the free electron laser. And this has now been demonstrated using a laser-driven accelerator, and it's possible to also develop plasma-based undulators, for example, the ion channel laser, and produce electron bunches with unique properties, narrow energy spread, attosecond pulse duration, and that gives the possibility of directly producing coherent synchrotron radiation. And of course, for high field science, because if we can manipulate laser pulses, control laser pulses and laser beams, one can then generate very large fields. So we can approach the conditions where not only electrons are relativistic, but also ions are relativistic, and the non-nonlinear QEG range. So lasers are large, like the Eli NP laser fills a very large room here. And part of the reason for that is because the components have to be quite large to avoid damage. And the scope of this activity, of course, is quite broad range, and this can be reflected in the growth of many facilities around the world for investigating these interactions. So if we collide two laser beams in plasma, we know we create a beat wave, electric field beat wave, and a magnetic field beat wave, and a intensity which varies if these are degenerate waves, equal frequencies. One produces a stationary beat wave, which has a periodicity of lambda by 2, and this applies both the transverse and the longitudinal force. And the longitudinal force, given by Lorentz force, can give rise to a ponderomotive force and expel electrons from the high intensity regions. So this is an example of the effect of the ponderomotive force, where the longitudinal ponderomotive force in this case, where the the force is proportional to the intensity and the square of the wavelength, inversely with mass. So it's much more effective on light particles and at longer wavelengths. So if you put a particle, let's say, at a position of 0.15 lambda relative to the center of this beat wave, you'll see the electrons oscillate longitudinally, and eventually the ponderomotive force drives the electrons out of the regions of high intensity. And depending on the intensity of the pulses and the duration that you apply it, you can drive these electrons into the regions of low intensities, into the nodes, antinodes. And so, and what's also interesting is that if you have colliding beams, these are degenerate beams in plasma. In gas, it's possible to preferentially ionize the gas in regions, in very specific regions, and make a layered medium. And if you use more than 2 beams, you use 4 beams or 6 beams, you can make two-dimensional structures or even 3-dimensional structures. So this shows you here the intensity of 2 counterpropagating beams, and for low intensity low threshold for ionization and high threshold for ionization. And you can see for a relatively high ionization threshold, you preferentially ionize the medium to produce layers of gas and layers of plasma. So in this, let me just see if I can put my mouse on. So if you have a look here, you can see this is at a point where you're just above the ionization threshold, and you can see that you're producing a plasma of a relatively cold plasma, in fact, of ions and electrons, which is interspersed by layers of gas. So this is a this layered medium can be used effectively as a diffractive element, both for scattering laser beams as a dielectric mirror, or even possibility of producing diffraction gratings. And what's really interesting here is that above an intensity, this is for two beams of 800 nanometers. And you can see when the ionization threshold is where the intensities are just above the ionization threshold of the order of 10 to the 13, 10 to the 14 watts per square centimeter, you produce this structure. And if the intensity is increased to 10 to the 15 or higher, the electrons in the plasma will start to be driven by the ponderomotive force. And you'll see on this is the distribution of the density of the plasma. So this color here is basically the background density of the gas or the plasma. And you can see eventually the electrons and the ions will start bunching. and they bunch, and this periodicity of the structure is lambda by 2. So this is a very, very fine structure. Plus, this is time dependent because you can see the structure gets filled in time. So you produce this volume Bragg grating. And if you use 2, 3, 2, 4, or 6 beams, you can produce either 1D layered structures, 2D sort of rod-like structures, and a crystalline structure here. And these are time dependent, as I mentioned to you. So we've been investigating their properties, and I'll tell you a little bit about that. But so the main creators forces of these are the ionization of the gas, and also the ponderomotive force. So the question is, why should you get an electron grating? Why should electron grating be created in the plasma? Well, we all know that the beat wave will drive the electrons into a periodic structure, periodic grating. This is the process also for Raman scattering in plasma, and this beat wave will generate essentially a layered medium of electrons on a constant background of ions, and the space charge forces of the electron layered medium will then apply a force to the ions, and the ions will gain a correlated momentum from the electrons. They hardly move at all. They gain a lot of momentum, and you can essentially switch off the electron grating, and the ions will continue to evolve into a structure. And because the forces of the space forces are very high, the electrons tend to follow the ions, and you get ion bunching basically that is very, very similar to the electron structure, but the peak density of the ion structure can be very high. Can be 10, or the electron structure can be 10 times the initial density, can be and above the critical density for the plasma. So space charge forces impart momentum to the ions, and then you just wait essentially, and the ions will evolve into the structure. So if the laser beams have different frequencies, it's possible to drive a Langmuir wave in the plasma and have an instability where the amplitude of the plasma wave will grow. This is the Raman process, which then gives rise to a backscattering of a pump pulse into a seed pulse, which is at a lower frequency, and through the excitation of the plasma wave. And as long as you match the energy and momentum conserved, you match the frequencies and the wave numbers, one can have a very rapid growth of the plasma wave. So this shows you what happens. The simulation I showed you there just shows you what happens when you have a monochromatic pump pulse. You have a very high gain increase of the plasma wave, and that gives rise to a relatively long backscattered pulse, which once the pump starts to become depleted, this will shorten. But if you use a chirp pulse, you can effectively preferentially scatter the laser pulse only at the point where they're resonant, where you meet the Raman resonance, where the wave, the energy and momentum are conserved, and you get backscattering of each Fourier component of the probe of the pump into the probe. And therefore, you can produce very, very short pulses in this method, using this method. So you have this distributed gain medium. You have to meet these conditions here, and to see Raman amplification. If you have a monochromatic beam, if you have a chirp beam, you get Raman amplification and a distributed gain. But at very high intensities, the ponderomotive force of the colliding pulses will trap the electrons, and when the bounce frequency of electrons in this ponderomotive potential exceeds the plasma frequency, you're in the Compton regime, which is the analog of the free electron laser regime, but in the laboratory frame of reference. And you can get basically amplification even in the case where you are detuned, when you don't meet the Raman condition here. And this we measured this many years ago, but the main point here is that you have to meet the resonance condition, and the bandwidth, the amplification bandwidth is very narrow for the Raman amplification. So we undertook a set of experiments where we wanted to study Raman amplification and vary the density of the plasma and of the plasma, and to look at amplification. And sure enough, for a range of densities in the pink region here, where you're meeting the Raman condition for amplification, you get some small amount of amplification, just a factor of 10 or so. And what was really surprising is that in the non-resonant regime, where you don't meet the conditions for Raman amplification, we saw a very large signal, which one would normally interpret amplification, but this didn't really make any sense because we compared negatively and positively chirped pump pulses, and you should, in the case where it's a Raman amplification, if you've got radiation at the right frequency, you would get the similar growth both for positive and negative chirped pulses. But we didn't. We saw a very large amplification here, and we about of the order of 20% of the fields were scattered back. And you can see on the bottom curve here where we were also with no seed pulse present, you get backscattering of fluctuations, backscattering off fluctuations in the plasma, just noise fluctuations. So turned out that for a positively chirped pulse, at the time when the probe enters the plasma, at the same simultaneously with the pump having passed through the plasma, that a plasma grating would be formed by the ponderomotive force. And what happens here is that after a few picoseconds, where the ions are bunched at, let's say, about 6 picoseconds here, this gives rise to a very large backscattering of the pump, which is passing through this region where this mirror is present here. And so we carried out some simulations here to try and investigate this, and we observed that about 50% of the pump, which scatters in this region here after 6 picoseconds, is backscattered by this plasma grating. And in this region here, where the probe and the pump overlap, the intensities are sufficient to be in the Compton regime, where you're in effectively the free electron laser scattering regime. And even though you're not you're not matched for Raman amplification, you get a significant amount of amplification in this region. And in the region before the probe pulse, you can see there's a lot of scattering from noise. So the pump pulse is continuously scattered from fluctuations in the plasma. And you can get a more than 50% efficiency of scattering in this region. So this is first evidence of the creation of these effective mirrors. These are multi-layered mirrors in the plasma. And it can be easily mistaken for Raman amplification. In this case, we are sure that it's not Raman amplification because we are not Raman matched because of the densities. So we undertook some experiments where we wanted to try and understand this in a more controlled way. So we used 2 short pump pulses, and we probed these pump pulses transversely. These layered structures transversely using a probe pulse. And we were able to demonstrate the formation of an ionization grating followed by a ponderomotive grating. And because these are time dependent, they make a time boundary, one can directly observe the blue shifting of the probe pulse through the plasma. I'll tell you a little bit more about that in a minute. But so if one has 2 pump pulses, which have a Gaussian shape, similar to what's shown there in the dotted red line, you'll see at this case where you're just meeting the threshold for ionization, you start to form this layered structure of gas and ions. And the density of this is just the background gas density, or the background plasma density. And you can see here, after some point where the intensity has grown, the ponderomotive force of the colliding the beat wave drives the electrons into a layered medium, and the space charge force of these then produces this momentum distribution in the ions, and they ballistically evolve into this fine structure. So you can see here that you start off with a density of 1, let's say, the relative density of 1, n naught over n over n naught equal to 1. And the density in these structures can increase to about more than a factor of 10 above the background density. And this is a very, very fine structure. The structure has comprises very fine layers, 20 nanometer layers of plasma interspersed by essentially vacuum. Yeah. And that's because at the high intensities, you more or less bleach out, you cause all the electrons to ionize. And what's more is because this is a structure which is attached to the ions, it's a very robust structure, and we've been able to, at least by simulation, demonstrate, show that this is robust up to intensities above 10 to the 18 watts per square centimeter, and it's not time dependent. So this plot here, on the left-hand side and the right-hand side, shows you the momentum distribution of electrons and ions, and then the density distribution down below. And you'll see on the left-hand side, the electrons will form this ion grating, which is a sinusoidal structure, which will then impose this very large electric field on the ions, and then the ions will evolve. And you can switch off the fields of the 2 pumps, and the electrons and the ions will still evolve to form this very dense structure. And the space charge fields of the structure can exceed 1 teravolt per meter, and the density of this can exceed the critical density for the plasma, electron critical density for the plasma. So the first stage of ionization, second stage is ponderomotive force bunching electrons. Third stage here is ions gaining momentum from the space charge force of the electrons, and the fourth stage is the ions inertially bunch electrons, ions dragging the electrons with them. So this is different from, for example, Brillouin scattering, which is has a feedback mechanism. This really does not rely at all on the presence of the pump to achieve the high scattering, the layered medium. So you can see here similar simulations, and you can see these, you're getting the structure forming here, and a very, very fine structure. And eventually the ions will move through the region where they're optimally bunched, and then they'll form a more complicated structure. So these are the experiments that we undertook, where we had 2 pump pulses, which were colliding in gas to form, first of all, ionize the plasma, preferentially ionize the plasma. They were probed by a probe pulse with an intensity around 10 to the 14 watts per square centimeter. Pump pulses had intensities up to 10 to the 15 watts per square centimeter. So you can see that the pump pulse intensity varied from 0 intensity through an intensity of about 5 times 10 to the 13 watts per square centimeter, the intensity that where the gas begins to ionize, and eventually to an intensity of around 10 to the 15, 10 to the 16 watts per square centimeter, where the ponderomotive force of the beat wave will drive electrons into the structure. So you can see here that you can produce this very, very fine structure. And what's really interesting here is that we produce a two-dimensional structure. So you maybe would ask the question, why would you see a two-dimensional structure in this case? This is not just a layered medium. This is a medium consisting of rods. And that's because the medium, the gas, is ionized by a combination of the front end of the pump pulses, which has an intensity of around 10 to the 13 watts per square centimeter, and the field from the probe. So you've got a sum of these three fields, and some of these three fields preferentially ionizes the medium to form a plasma, which has a two-dimensional structure. So to study this, we probed using a probe pulse, which is circularly polarized. What we wanted to do was to probe the structure parallel to the layers, so we could observe the birefringence of the medium, because the fields pointing into the layers will have a different permittivity from the fields which are aligned with the layers, surface of the layers itself. So therefore, one would expect the the phase velocity of the laser pulse to be different here, and therefore birefringence. And sure enough, by changing the delay of the probe, we were able to probe the time evolution of these structures from the point where you get ionization creating the structures to the point where you have the ponderomotive forces creates these structures. And by using polarizers here and wave plates, one is able to then measure the different polarization components. And what we observed here was evidence of amplification of light, which occurred at the point where you meet the condition for ionization of the medium to produce this rod-like structure here, you can see. And then followed by these are the energies of these two beams for the two polarizations. And you can see here we have evidence of the birefringence of the medium. But what was really interesting here is we had evidence of the amplification. And the amplification occurs because of the the two-dimensional structure here, which is a time-dependent structure. And we were able to then, by measuring the energy ratio of these, we were able to measure the phase change of the ordinary and extraordinary waves going through the structure here. And we were able to show that we had about a pi/2 phase delay, and therefore the medium was birefringent. And not only that, but because this media here is a three-dimensional medium with an intensity which varies three-dimensionally, where the beams collide, the time dependence of the formation of the grating is also time dependent, and therefore you get a lensing effect, because you get a grating here, this two-dimensional grating, which is formed, it takes different times to develop, depending on the radial position inside the gas jet. So therefore, this produces a lens effect, and this is a time-dependent lens. So we're able to show that this lens was acting as a negative lens here for a period of around 1 picoseconds. So anyway, so that's basically the end of my main part of the talk. And the other one really is just to do a bit of mentioning our work on at setting up a facility at Strathclyde. So we have a fully operational facility at the moment with 350 terawatt laser, 40 terawatt laser, and a half a terawatt laser, and an area where we can. So to conclude, there's a need for the optical elements. We can make these optical elements, both a mirror, a wave plate, and a lens, and we can go to high intensities. We know from simulations that these can withstand intensities above 10 to the 18 watts per square centimeter. They are 1D, 2D, 3D, and even 4D structures, if you consider time as one of the dimensions. They're novel studies of matter, and the inertial bunching of the ions makes them very robust, and there are many new opportunities. So I'd like to thank you all for your attention, and just to acknowledge all the collaborators on this. I wasn't able to list all of them in detail, but this work has gone on. The Raman application work started 20 years ago. So this is really the next evolution of our studies. So thank you very much.
Thank you, Dina. You're perfectly online, on time.
Okay.
Okay. And we have time for questions.
No problem. Yes. Katerina.
Yeah. So hi, Dino. First of all,
Hi,
thank you
Katerina.
for a super nice talk and very, impressive experimental results. So I have two questions.
Yeah.
One is that you made the point is not Raman, and I agree with you. But is at this point, why is a chirp even necessary, and why don't you just use two identical? Without the downshift, just two identical.
Well, we do use two identical chirp pulses. So the reason why we use them, the obvious reason normally is because that's the only things we had.
Yeah.
So obviously, if we had two picosecond pulses, monochromatic pulses, we would use that. But we did these experiments at Rutherford Apton Laboratory and used their Gemini laser, which is essentially chirped. And also we wanted to observe the transition from Raman to this case where we're making this plasma mirror in the middle of the plasma. So what was really a surprise of it is how efficient the scattering medium is, and actually how there's a lot of, well, actually not a lot. And Katerina, I know you've done quite a lot of work on at least the brilliant side of scattering of this. There's been a lot of reasonable amount of work over the last decade or two, and it's quite easy to misinterpret your results. And so I think one of the messages of our results is one has to be very, very careful interpreting your data.
No, the results are really nice, and maybe a bit of chirp helps actually. We did some work on that. Some chirp will help, but you don't need. And the second question is simulation and hopefully the experiments. It was called plasma limit.
Yeah, cold. We didn't heat the plasma. We ionized it directly with the laser beam. So, and what was really interesting is we could observe both the ionization creation of the gratings plus ponderomotive creation of the gratings.
So just to, since like you said, we worked a lot on that. It was kind of interesting to see what stops the growth. That is this, like ion X-way braking or ballistic motion, whatever. Depends on the regime. So we did some simulations where we studied actually what happens if you introduce a bit of temperature. So maybe
So
that, and there is a continuum. So I think it's like you say. I think the message, the get-home message, is these are really robust.
I think this is this is the way, if you want to build an amplifier, a scattering medium, which is essentially what Raman amplifier is, or even Brillion. This is the way to do it, because you can decouple the bunching mechanism from the scattering mechanism.
Right.
And this is very, very robust.
Well, but you should, I will send you a paper when we look in detail at the temperature effect.
Yeah, sure.
Thanks a lot. It was super nice.
But in fact, the temperature effect is one of the reasons why we only see the scattering for a positively chirped pump pulses. For a negatively chirped, the scattering is very low.
Okay.
And that's because the plasma is basically heated by the medium.
Right.
For the negatively chirped pulse,
It makes sense, and it's what you find from models. Okay, thanks a lot again.
No, pleasure. Yeah.
Do we have other questions? If not, thank you, Dina, once more.
Okay, thank you, Sergey. Good to see you all, and Christoph. And Okay. Okay. I'll stop sharing.
What do you like to say?
You just get stop sharing. Okay.
We have a presentation by Stefan Ataman about all optical vacuum birefringence with petawatt class lasers, case study for the LPHYS parameters.
Can you hear me and can you see my screen?
Yes, we see it. Let's do it. You have 20 minutes.
Okay, thank you very much. Okay. So, presentation, as the title says, is basically about possibility to use power petawatt lasers in order to measure vacuum birefringence. And I acknowledge contribution from the whole team. So my talk will be structured, it's a short introduction in case people don't know what I'm talking about. Then I'll discuss some other proposals and experiments that have been done. I'll then discuss some technicalities about the vacuum birefringence in an interferometric scheme. And finally, I'll show some sketches about how we think to make this experiment here at LIMP. So when we are interested by a vacuum phenomena, typically from the QED Lagrangian, we do what's called integrating out the fermionic degrees of freedom, and we arrive with an effective theory. And we arrive at this horrible expression, which is the Heisenberg-Euler Lagrangian. And the only reason I show you this slide is to be on the same page with my notations, the F and G invariants, critical fields, and so on. So what I will actually use is this lowest order approximation, where we have the Maxwell term, and then we have the QED corrections with a coefficient, which is pretty small. And we could even generalize this Lagrangian and put some just coefficients C1 and C2. For example, in the Born-in field theory, we have a different prediction, and there are some fans of the Born-in field theory due to its connection to the string theory. So what are the predictions? Well, plenty. I'm discussing only vacuum predictions, so no pair creation. Light by light scattering, quantum vacuum, reflection, diffraction, and so on. And then quite a bunch of nonlinear phenomena. By this, I mean photon splitting, photon merging, four-wave mixing in vacuum, and so on. And finally, vacuum birefringence, which is the topic of my talk. I just want to mention that, for example, the Born-in field theory has light by light scattering, but predicts no vacuum birefringence. So the name of the game will be a probe, which is weak compared to a background, which we'll call pump. And so classically, it just propagates through. Quantum mechanically, it will be some interactions, and that's what gives interesting physics. So I go straight to vacuum birefringence seen by a probe beam in an electric and magnetic field. So we have generally three terms: the Cotton-Newton, which is the magnetic term, the Kerr effect, which is the purely electric, and then we have a magneto-electric effect. Now, I already assume the geometry that's favorable here, like the E and B fields are perpendicular to each other, and they're also perpendicular to the probe. And already from this one, we can see some effects. For example, what we achieve today as maximum E fields give a quite weak signal. So there are, to the best of my knowledge, no E field based experiments. There are some proposals, Colombo assisted. Practically all performed experiments are in the B field region, and there are a bunch of them. And now there's this new trend of using the petawatt lasers because we have these intense fields. And so the refraction indices are much higher. So I'll start with the purely magnetic background. Now, Mother Nature gave us some example with this neutron star that was observed. Not everyone agrees, so I'll not comment on that. Earth-based experiments are all based on a cavity and a laser, a resonant cavity, Fabry-Perot, and then with a laser and in a magnetic field. I'll discuss about them in a minute. And then there are proposals with using gamma rays and still in a magnetic field. Now, if we have a laser probe in a magnetic field, it's easy to compute this vacuum birefringence, and for reasonable fields, we get something like 10⁻23 as order of magnitude. And this was the task of the experiments that tried to tackle this really hard problem. And to the best of my knowledge, these are the best results that were obtained. So PVLAS reported a factor of 50 above the QED limit. That is the best they achieved, which is in itself a phenomenal result. Now, if we switch to a laser field, things get much more interesting. We can do some simplifications and we gain a simpler expression, and then we can, for example, discuss the case of LPHYS' 10 petawatt laser. So in function of how focused the laser is, we get something in the order of 10⁻10. And that's already 13 orders of magnitude above the magnetic only scenario, which makes detecting it much, much easier. So what experiments have been proposed for vacuum birefringence with the pump laser? Well, gamma ray probes. I'll start hard and I'll go soft. So gamma ray probes, where typically what we're looking for is the polarization flip. So this is gamma polarimetry, not an easy task. There were some proposals, quite a bunch of proposals in the X-ray domain. This is a very interesting domain where polarimetry is much better and the effect is still quite strong. Then there were quite a bunch of proposals of all sorts of vacuum reflection, diffraction, and other phenomena. Quite a bunch of them. I cited only a few. And finally arrived to this all optical, where we try to see interferometrically to measure a time delay. So the proposal I will discuss today is this Mach-Zehnder-based interferometric scheme, where we have a pump laser that will meet a probe beam that's itself in a Mach-Zehnder. And so it will counter-propagate on a given region. I'll discuss in detail in a minute. And this will create a phase delay. And interferometry is quite a precise. We know how to make quite precise measurements with interferometry. So this could be potentially interesting. So when we have a pump and probe lasers meeting, the probe will see a disturbed vacuum over roughly the distance of the pump. And so it will accumulate a phase that can be calculated and depends on the refraction indexes, perpendicular and parallel, which I mentioned previously. So if we make the difference between this and the same wave propagating through a non-disturbed vacuum, we get this final expression. And if we plot it, we get this graphic. Now, I also plotted Beamline's 10 petawatt laser, the L4, which is roughly our laser, however, 6 times more energy and 6 times longer as pulse. And I'll discuss also what importance this has. So roughly, as order of magnitude, considering that we don't want to focus the laser too much, let's say around 3 microns, what we expect is something around 10⁻8 as order of magnitude. Now, what question is what should be tau p, the pulse duration? What's the ideal duration? Now, I'll take the very non-favorable case where they don't meet much. They meet exactly in where the pump hits the hottest spot. So then there's not much overlapping outside this area. So basically the probe and the pump should have exactly the same duration. However, there's a second more favorable case. If we manage to make them totally counter-propagate, I can make the assumption that with a longer probe pulse, I can take advantage of the fact that, assuming that this is a Gaussian beam, I have this twice Rayleigh length, or the depth of focus, where the intensity is roughly constant. It's not really constant. I have to divide it by 2, but as a first approximation, I can see it's constant. So then if we make the calculations, we arrive at an ideal duration for a totally counter-propagating, something between 100 and 700 femtoseconds, which is much longer than the 25 femtoseconds of our laser pulse. Now I switched to interferometry. So I changed the question. I know the QED tells me do 10-8 radians or better. And now I say, fine, I have an interferometer. This is my target. What should I have? And generally, the metric is in function of the average number of input photons. Now, I know the pulse duration. We just discussed the two cases. So I can compute the probe power that's needed. So here we arrive at interferometry. So we have two scenarios. One, when I use shot noise limited interferometry, which means classical states of light. That means a laser. And I have the famous shot noise limit. So I want this to be better than the QED imposed limit. So we arrive at an average number of photons, which should be at least 10^16. If I go to this very elusive Heisenberg limit, I'll discuss shortly about it, then we have this 1/n instead of 1/square root of n limit, and then the number of photons is obviously 10^8, a very optimistic scenario. So basically, if I'm using a laser, that's a coherent light, the shot noise limit will apply. And if I crank in the numbers, these are the powers I'm getting. I'm putting a limit at 3 microns because probably we can't, but we also do not want to focus more than that. So in conclusion, at least for ELI-MP, for 10 peptide pump, the probe power should be something like 0.01 to 1 terawatt. Now it depends if they are really head-on or if they are nearly head-on. The difference is huge, orders of magnitude. The difference is not so important, for example, for ELI beam lines. And the explanation is that that pulse is so much longer. And so the fact that I can have a longer probe pulse doesn't play such an important role. Basically, you do not gain much. But for us, it is a huge difference. Now, if I just for fun, I go for this Heisenberg limit, then powers are ridiculous. I mean, I'm talking about kilowatts or even lower than kilowatts. And there are many funny things that happen. Probe power does not depend on the probe wavelength. For perfectly head-on, it doesn't even depend if it's focused or not, but these are just artifacts. So to become realistic, I mean, how could I reach this Heisenberg limit? I could use what's called noon states. I need 10^8. I mean, anyone in a quantum optics community would simply laugh. I mean, the record today is something like 100 in very difficult conditions. So nowhere near. I could also think of using coherent plus squeezed vacuum, but here again, I'm totally out of any reasonable bound. The record today is 20 dB of squeezing. I would need 85 dB of squeezing. I mean, this is totally outside any reasonable limit. However, I don't have to chase this limit. We can go to what's called sub-shot noise limited. And so I can use these famous squeeze states of light, and I can enhance my phase sensitivity, realistically speaking, by a factor of 10. What technology we have today, that's what we can expect. And this is not science fiction. This is actually happening as we speak. LIGO is running a new run, and they have now a squeezing of 6 dB, and they expect to reach 10 in the near future. And what you see in the right is, for example, in green, this is the quantum enhanced sensitivity of LIGO. And LIGO is a very interesting case study where just cranking in more laser power would just degrade the performance. Their only way to enhance was to use non-standard methods. And they use this squeeze light. And in the last run, they managed to have from roughly 2 events per month, more than 8 per week. So this is just due to squeezing. So returning now to ELIs and plans. So we have 2 options. Either we go head-on, then we need necessarily to have some sort of SAG to have 400 nanometers. Then we can take advantage of the longer probe wavelength. And then we can have much lower powers, something in the order, let's say, of 40 gigawatts. If we go at an angle, I'm taking the worst case. The big advantage is that the probe doesn't have to be frequency doubled, so we can use the second laser for that. Then we have a higher number of photons, and the power should be something around 1 terawatt, which is still reasonable, but it's much higher and it puts much more strain. Okay, so a possible geometry for, let's say, at an angle, the nearly counter-propagating would be something like this. So the 10 petawatt is just focused, and then it will just go into a beam dump. And the second is our second laser, which we pick a part of it and put the polarization at 45 degrees. I explain in a minute why. And then we form a Mach-Zehnder, and you see one arm is just propagating, the other one is meeting the laser. One exit will just get into the beam dump and probably a camera to make some monitoring, and the other one, which will be the dark port, has a PBS and 2 detectors. Now, in the perfectly counter-propagating geometry, we need to use the dichroic mirrors. And so the 10 petawatt pump will just reflect from the dichroic mirror of axis parabola and back again and then into the beam dump. And here is compulsory the second harmonic generation. We again have the polarizing thing to put it at 45 degrees. And then basically we have exactly the same thing with 2 detectors, a PBS, and so on. Okay, what do we measure? So at the output, we have the average number of photons. Now, in order to take advantage of an interferometer, we have to put it what's called a sweet spot or the working point. And in this case, we have to put a phase of pi. And then I can make some approximations knowing that my signal, the green signal phi s, is a QED induced signal. And then I do some just Taylor expansion and I get an expression that's quadratic in phi s, which is not necessarily great, but we're not yet done. Then, of course, we can just, for fun, we can compute the variance and apply the error propagation formula, and we get exactly the shot noise limit, which is pretty much what we expected. So, of course, we'll not get just a signal. We expect vibrations, and at one point, we can't control them. We'll try to put some attenuation, but they will be there. So let's call this a phi d, like a displacement. So my signal will be actually the actually QE this signal, QED induced signal plus the vibrations. I'll totally ignore the phi s squared signal, which is small. Now, the crucial point is that during the relevant time, that's the probe time, I assume the phi d is constant because vibrations are typically low in frequency, let's say kilohertz. I'm talking about picosecond at worst. So after the PBS, we have this ratio. However, since phi d is simply not moving and phi s is rapidly varying after a low-pass filtering, if I take the ratio, the phi d drops out and I just get the signal I'm looking for. Now, what's interesting compared, for example, to polarimetry, in polarimetry, typically you measure the difference of these coefficients, which come from the Lagrangian I showed you before. Here, I can have direct access to either the ratio, that's easiest because I don't have to bother to estimate them, or I can individually measure them, but then these vibrations need to be estimated, and we also have some ideas how to do it. I could answer some questions if there are on this. Now, what I showed you today is, let's say, an order of magnitude. I made a bunch of approximations, so I didn't really completely model the interaction with the pump and the probe. So we might use some software that can tackle these issues. We are still to do the evaluation of the signal from the residual gas. Some effects we expect from the Mach-Zehnder, like the beam splitters are not really 50-50 and so on. And also a complete noise budget of everything that we expect to disturb our vacuum. This is either ongoing or not yet started, but we're in the process of doing it. So to conclude, an all-optical vacuum birefringence measurement with a 10 petawatt seems feasible in the near future. Many challenges remain to be solved: the pump probe synchronization, vibrations, signal from the residual gas. Now, possible enhancements includes putting squeezed vacuum, which is routine already. A second enhancement would be squeezing the laser, which is much harder. It has been proven, but it's much harder. And then if detection is achieved, what's interesting about this experiment is some headroom for enhancement. And then we can think about if we mastered it and we could, for example, just crank up the power or just put some squeezing and see better these parameters. And if ever we find some deviation from QED, this would point to new physics. So thank you very much, and questions are welcome.
Thank you very much for your presentation. We have a little bit of time for the questions. Do we have the questions?
Or remarks?
Yeah, can I make a quick comment, maybe?
Yes, please.
Yeah, thanks for the talks. Very, very interesting. And as you know, this is one holy grails, let's say, of the field, especially experimentally. We did with, for instance, with a group of Christoph and with Antonino and so on. Back in the day, we did try to do some estimates of trying to measure similar effects in the laboratory. And the predominant issue that we find is exactly the noise coming from non-ideal, let's say, ideal scenarios. One of them is the non-perfect vacuum in the chamber. So, and as you mentioned at the end of your talk as one of the things that you're going to address, my question is how you're planning to address that or to model that?
Well, I think if Yoshihide is online, he can really answer you because we discussed extensively. But we have some ideas.
Yeah.
Well, differential pumping is one solution. Well, first of all, we don't know exactly where we'll perform it, in what area, because if we could perform it in an area where we can do a better vacuum, it's easier. If not, there are some solutions with, for example, a strong UV laser and then some very strong electric field so that you ionize and so on. So I saw such proposals. But yeah, we plan to start slow with just an interferometer and evaluate how well we can measure first this without any laser, any signal. Yeah. And then we just crank it up and we see how far we go. I mean, I know it's ambitious, but since we have the laser here and everything, I mean, it's kind of asking to be tried.
No, of course it has to be, if you don't try new things, you don't find new things. But one thing, for instance, that you could consider is ponderomotive cleaning. So if you have a laser going through the area or the focusing area, you can actually ponderomotively, you can ionize the residual gas and ponderomotively clean it.
Yeah, thank you for this suggestion. Yeah,
evacuate. Just a suggestion, just something you can try.
Yeah. I mean, any suggestion was welcome because, yeah, probably the first time we'll try it, at least as a test, we'll be horrified and then we'll just optimize it.
Yeah. I guess it's more of a question to Gianluca. What is any estimation for the required vacuum level?
Depends on the laser. So I don't know for the 10 petawatt we need to see, but we did find that the requirements are usually very, very, very stringent. You're looking like 10 to the minus 9 millibar or something, but it's just a number, okay? Which is not impossible, but it's not simple for a big, for a big vacuum chamber.
I mean, I think we reached 10⁻⁸ in the smaller interaction chamber, but not in the big one. So
yeah, but then you have wind. Yeah, but if you do differential pumping, then you have windows that you have to go through. So you have other problems. if you have a smaller chamber inside a big chamber, you have to go through windows and stuff. Ponderomotive cleaning could be, I would look into that.
Yeah. But Christopher, we don't hear you. Unmute you, Christopher.
I'm sorry, I got it. So I also enjoyed your talk. I mean, very interesting things also.
Thank you.
This is squeezing and so on. So, I mean, at the end, of course, we all hope, of course, that the theory and the experiments do not match, right? But for that, I'm sure you're aware that you have to be even more accurate, right? I mean, this would be worthwhile to, of course, estimate. There would be something for theorists, right? To see, what the new physics, what are these deviations we expect from new physics, right? And I mean, these are things, we are involved, for example, with highly charged ion experiments. I mean, these are, that would be the next step, I guess, to think of, the various new physics that could appear, and then, of course, make the estimation and to see for your experiment, sort of what is the accuracy you need to resolve this new physics. And I guess that would be even another step of challenge for you, right? I mean, of course, at the moment, the first step is to see this, to detect this, vacuum fringes. But I guess the next
step, you're totally right. I mean, this is this is far away. This is far away.
But for your planning, I mean, if you sort of think of this, long term, then I guess it would be really worthwhile to sort of, go a few steps further with the, accuracy of the experiment, and then sort of not just, look for the detection, but really go to the next step, be so accurate that you could resolve. I mean, this is, of course, something for us, right, to really estimate sort of for all these different suggestions of new physics, for each, dark photons and axions, whatever, you could imagine, and what sort of deviations you would expect. And then, of course, the demands on you would be even a step further. That's, but of course,
for sure.
And I think it's another encouragement for you to do it, right? I mean, that's
of course, that would be the biggest encouragement to do. I mean, I would really be happy just with QED. I mean, I would be extremely happy to see 7/4 the ratio, and just confirm QED. I would be extremely happy. I mean, really happy.
Yeah, that would be the first step.
But going beyond this would be, and what's encouraging here is that you can crank up the power if you're in a favorable scenario. So of course, when you reach when you reach 100 terawatts, you kind of get to the edge. But when you are at 1 and you can go to 10 and so on, you can go higher. And you have this squeezing. I mean, squeezing is an amazing technology, and I admit, I mean, this is another type of squeezing compared to LIGO. It has to be much more broadband, and probably we need to collaborate with other people who have experience and to build the source. But when you are out of options with your laser, this is like you're an ace in your sleeve. I mean, just you have a joker. You can say no.
I like it. It's a good joker. Yeah, I like it. Yeah.
But for the time being, we'll fight noises. We'll fight the residual gas. I mean, this is the first task. So. Yeah.
Okay. Great.
Do we have further questions? If not, the session is over. I thank all the speakers and audience. It was very interesting to listen to these presentations. Thank you very much.
And don't forget, the next session is in 20 minutes, right? So, so we have 2 more speakers, right, Gianluca?
3. We got
3 more. Great, great.
Yeah.
Okay, I just missed it. Okay, good. Yeah. So see you then in a bit, hopefully.
Yeah. So I'll see everybody at in 20 minutes, and I'll share the next session.
Yeah. Thanks a lot.
Okay. All right.
Have a good break. Yeah. Bye.